Today we're going to try something really crazy. 23.9, close enough. These are very close to true O scale. You don't want to try this with a modern transformer. So this is based off of a real B&O caboose from 1916 up to 1938. That is not helpful. Now it is truth or consequences time. Part of the circuit is running through this wire arm here. Very simple but effective animation for the layout. Hello again, this is Mike with Toy Train Tips and Tricks, and today we are looking at Lionel's O27 remote turnouts and how they can be modified to run off of constant voltage rather than track voltage. So we're going to look at three things. One, how are they normally wired up? Two, what is the advantage of wiring them for constant voltage? Three, what are the disadvantages to wiring them to constant voltage? And then four, how do you actually accomplish the thing if you decide to go forward? So, Lionel switches, starting with the 1122 of 1952 all the way up to the end of O27 track production around 2000 or so. We're very similar. These are post-war switches. This is MPC era, 1970 and later. They all shared certain features in that they were wired to run off of track power, the same power that runs the trains. The center rail powered the hot of the solenoid. The outside rail powered the common, and there was no way, easy way anyway, to hook these up for constant voltage. Unlike their O-gauge cousins, which you could plug in a constant voltage plug and run them that way. O27 switches you could not. But they were designed to be simple and easy for beginners to use. You just put it on the track, hook up your three wires for your controller, and you were ready to go. So, why even bother trying to switch these over to constant voltage instead of track voltage? Well, the biggest reason has to do with how quickly the switch itself throws. If you are switching, you're running your train slow, and you need to run the turnout, the low voltage going to the train to make it run slowly also means that your switch is going to throw slowly or possibly not at all, causing a derailment. That's a problem. So the easy way to fix that, rather than cranking your train all the way up to maximum voltage every time you want to throw the switch, is to set the switch so that it runs off of a constant voltage of somewhere between 12 and 16 volts, depending on your tastes and how quickly you want them to snap across. 12 volts is usually sufficient for these. Some people like to really crank them over at 16. It's your choice. Somewhere in that range should work. If your switch still doesn't want to throw at 15, 16 volts, there's probably something else going on with the mechanism causing that problem. Most Lionel switches throw really well at 12 volts. 12 volts is fine. So whether it's a post-war switch or whether it's an MPC or modern era switch, they share some common features, how they're wired up, and switching them over is the same thing. Oh, sorry, the disadvantage. We talked about the advantage. The disadvantage is if you're set up on constant voltage and a train stops on the switch, the whole time that the wheels are making contact with your outside rail, power is going to the solenoid, and this could lead to burnout of the switch motor. So if these are going to be on a location on your layout where a train is stopped frequently, you may not wish to go ahead and do this modification. Or there is a workaround. This is an advanced technique where I'm not going to go into here, but it is possible to wire these up to use DC voltage and a capacitor discharge unit, so that when the wheel hits, a lot of voltage flows through immediately, throws the switch, and then that capacitor doesn't recharge until after the circuit has been broken, after the train is moved, then it recharges. I said that's a more advanced technique. I'm not going to go into that here. I've never done it myself, but I know it is possible. All right, so you decide you're going to switch these over to constant voltage. what's the process? Well, let's take a look at this one because I've already done the process here. Notice I've added a fourth connector here. And you could probably use a longer bolt than what I use, but I'm going for function over form, so it's not pretty, but it works. So with any of these, the first step is to remove the back, this bottom plate, from the turnout. And what you'll notice, I'm kind of going to give a general overview, because over the course of production, things changed. On some of these, there are bolts or rivets that need to be removed, but they're not on other models. And some have more, some have less, some have them in slightly different places. So the general overview here is if there are rivets that go through this back metal plate all the way through to the top plastic, they need to be removed in order to pull the turnout, to remove the back off of the turnout. So likely locations are here and here, although on this switch, this one was left open so that you could use that to nail down the track. But sometimes there's a rivet there. Sometimes there's a rivet here, sometimes not. Like on the MPC version, there's not. On this post-war version, there's a rivet here that helps connect the switch motor to the plate. Actually, it wasn't on this one, but it is on this one. So again, there are changes. So this one had a rivet, this one never did. So I didn't have to worry about removing that one. Sometimes there's a rivet here, which is for the common post, and sometimes it's left open and it's just riveted to the plastic base underneath. But sometimes it goes all the way through. If it goes all the way through, it needs to be removed in order to get the panel off. So how do you remove these rivets? Well, there's a lot of different methods. You can use a grinding tool, a Dremel tool, a drill bit, a drill on slow, which I tend to use. But whichever method you use, you basically just want to remove enough of the backing rivet material so that you can pop this this off. Now there's one that's very, very important that you go slowly, and that is the rivet that goes here, here, here. This rivet goes all the way through and is actually the backing of the frog of the turnout, this piece of track right here. So if you go too quickly, say with a drill, and go through and come all the way through, you can permanently damage your turnout. So with this rivet here in the middle, it is vitally important that you go very slowly. Just remove enough of it so that you can get the back off. You want it to still be attached to the next layer, the plastic, if at all possible. If you cannot, then you'll want to reattach it to the plastic using an epoxy or something like that, so that that frog of your turnout is not there. So the rivets are the first step. The second step is anywhere the outside rails attached to the backing, you need to bend these tabs up and out of the way. And again, through the course of running, of manufacturing these, it changed. Here you've got 2, 3, 4 connections. Here you've got 2, 4, 6, 7, 8, 9, 10, 11, 12 connections on this one. And on the MPC version, 1, 2, 3, 4 connections. So it changed, but the general rule, anywhere where you see the outside rail coming through, those tabs need to be pulled up. If for some reason you see the center rail here, you notice it only goes through to the plastic, not to the metal, leave that one alone. Okay, so I've removed all the tabs, I've removed all the rivets, and we can pull the back off of this one. I've already done that. And what you will find is some sort of insulator, usually paper or some sort of fiber, and that gets you to the innards of the turnout. Just like with the rivets, the way these are actually wired up changed throughout production, but what you are looking for is a wire that comes right here. This goes to the center of your switch motor, center of the solenoid. This is your hot power, and it is going to be connected somehow to the center rail. And you notice in this case, it was soldered to this copper bar, which comes over here, and there's a bracket, and right here, these are connected to our center rails. This is outside rail, outside rail. These are common. Don't have to worry about those. This is the center rail. This is hot. And this copper bracket, this side, goes up and supplies the hot to the light bulb in the switch motor. Obviously, the MPC models that don't have a light bulb won't have that copper strip. So you're looking for, where does this hot come off of here? And so if you've got this copper strip, you've got a couple of options. One, you can disconnect it completely. And then I added this red wire. We'll talk about that in a moment. If you disconnect it completely, the disadvantage is now you no longer have power going to your light bulb. Or you can leave it connected, or in this case, I'm going to reconnect it with this additional wire. But you'll want to cut this copper strip somewhere in here before it reaches here. And by the way, this just pops right out. So you can completely remove it if you wish, but you notice there's a little channel that this sits in. So just cut this end off so that it stops right about there. Reinsert it into the channel. That part is gone. This is still your hot, and then you can leave this wire and then attach a new wire either to here or anywhere along your remaining copper strip. Now, where's that wire going? That wire is going to go to a brand new connection post. Here I used a number, let me make sure I get the package right, number 6, 32 by 3/8 inch machine screw. You could use a longer one to match the height of these if you wanted to, but again, function over form, that's what I had. So we've got the head there. I drilled a hole, a 3/8 inch hole, put the machine screw through, put one bolt in the bottom to hold it in place, added a second one where I can attach the wire. This, running a wire off of this, connecting it to the hot, this now provides constant voltage hot to the turnout. The common here, I was originally thinking about removing that, but if you notice, this metal plate here serves as the mounting for the switch motor. It also supplies the common to the switch motor. So I really can't remove this, or I can't rewire this to be the hot because it's connected, it's physically part of the switch mechanism. So this becomes redundant. You don't need it once you've got track power hooked up to your common, or you can use it as an extra feed of coming from your transformer or coming from your common bus to provide extra common connection to your track. You can use it for that, or you can leave it blank. It won't make any difference. These two posts remain the same. They will control the direction of the turnout. But by putting your constant voltage, either the accessory side of your transformer or a second transformer that you can phase to your others on your layout, just to provide that constant voltage, put the hot there, and you can either put the common there or use the common bus off the track, and you are able to throw these off of constant voltage. So again, you're going to add a post, run a new wire to it, connect it to where the hot is, either directly to the switch, or if you want to keep the light bulb, cut off part of this copper, put it back in with the light bulb, reattach it here, and then maybe use an epoxy or something to hold one end of this down after you've cut it off. And there you go. Reassemble the switch using small machine screws. I'm going to use number 440s, 3/8 inch, to put it all back together. I'm also, in addition to using the original insulation plate, I'm going to add some electrical tape to cover up anywhere where there could possibly be any interconnection between the hot and the common. Like I'm going to cover that and that and my new connections before I put down the insulating plate, run my new machine screws through the backing, reattach the tabs from the track, and I will be ready to roll. So reassembling this, you are then ready to go with a constant voltage turnout. And like I said, because there were differences, even as you saw with the rivets, there's also differences in where the wires are attached as they did different production runs and different changes. So yours may not exactly look like this when you open it up, but we're looking for the general principle. Find the hot wire, the center of the solenoid. If it's got a light bulb, that's going to help you find it. And attach there. Disconnect it from where it attaches electrically to the center rail. Reattach a new wire, a new post, and you are ready to roll. Wire your hot here, your common here, and these two control your switch. And then you've got it. You have constant voltage. You are ready to roll, and you can do your slow switching in your yard without having to worry about your train flying off at 100 miles an hour while you are throwing your turnouts. I hope that helps, and I will go ahead and I'm going to be doing the same thing to these. And this MPC turnout actually needs a lot of TLC in addition to switching it to constant voltage. It's got some parts missing, so when I do this one, I'm actually going to do a video showing how you can use a manual turnout as a parts donor to get a less than ideal remote turnout working again. So that's all for now. Hope to see you next time. I hope you enjoyed this. Tell your friends, tell your neighbors, like it, share it, and please subscribe. And we'll see you next time on Toy Train Tips and Tricks.